Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at computer forensics, to pull back information on the computer your application is running on. Some of the applications you write in PowerBasic may not be running on your own computer. So it's useful to know something about the computer your application is running on. And that takes us into the world of computer forensics. The first thing it's useful to know about the computer is the name of the computer. So we're going to be creating a new library called PC Info. And in here we're going to be putting the routines to pull back information about the computer. So the first thing we'll create is a routine to pull back the computer name. So we're going to create a function called PC computer name. Now, like anything, there are easy ways and hard ways of performing this task. The easiest way to perform this task is to use the environment variables. Environment $$ will return one of the environment strings. You just have to tell it which one you wish returned. And in this case, we're looking for the computer name. And this simple one line of code should be enough to return the computer name. So as we've created a new library, we'll need to put an include in for it. And if we run that now, it will return the name of the computer we're currently running on. Now there is a more verbose way to pull back the computer name, calling some of the Windows API, but generally this will work on everything from Windows 7 onwards. So unless you're running on a really old computer system, this will work nicely. So having got the name of the computer that your program is actually running on, it's now useful to find out what's the username of the user actually running your application. You may wish to permission your application or parts of your application based on the user that's actually signed into the machine. So the next thing to do is we will return the name of the user. And we'll create a new function to return the username. Now, as before, there is a traditional Windows API call called getUsername, which will return the username for us quite nicely. But we're going to use the environment string again to pull back the username, making the code very straightforward and saving a Windows API call. So this will then return the username of the user. And there we are. Very straightforward and very easy to use. So we have the name of the computer and we have the username. Depending on the environment, the application may be running on a computer connected to a domain, or it might be completely standalone. One way to find out is to determine the domain you're connected to. And we will create another function to return that. And just as we did before, we're going to use the environment $ again and return the user domain. And if we run this, we'll see in this case it returns the domain as being the same as the computer name. So that tells you this computer is not connected to a domain. If it was connected to a domain, the domain name and the computer name would be different. So we now know a little about the computer we're actually running on, but we'll want to know more. Another useful piece of information to know is how much memory has the computer. It may well be that your application has a minimum specification, and you may want to check the amount of memory in the computer before your application runs. So we'll create a new function to get the memory. Unfortunately, unlike the previous commands, there's no environment string we can actually pull back to tell us how much memory is in this computer. We're going to have to do this one the hard way. So we're creating a local variable called urmem, and this is going to be created as a user-defined type, which is one of the Windows API user-defined types. And we're going to take that variable and we're going to set the length as a D word. Basic to work out how big it actually is. And the Windows API call we're actually doing is to global memory status X. And we're passing a single parameter, which is our user-defined type, into which it's going to populate this information. And that will be returned in this element of the user-defined type. However, this is returning a number which is in bytes. So what we'll want to do in this one is we'll want to divide this by 1024 to get it in kilobytes, and then 1024 again to get it in megabytes, and again by 1024 to get it into gigabytes. And then, so we get a nice round number, we shall round that. And we'll want to turn that into a string so we can return it to our calling routine. Assuming I've got all the brackets in the right place here, we should be able to return that quite nicely. So, have I got the right number of brackets? No, I don't. What have I missed? Oh, I missed out the rounding value. What we wanted is to 0 decimal places. One too many brackets. So this tells us we have 64 gigabytes of memory on this machine, which is indeed quite correct. So the other thing we might want to actually work out is how many processors we actually have on this machine. So we'll create another function to pull that information back. Now again, there are two ways of doing this. You can use the Windows API calls, which would effectively be this. Or we can quite happily use another environment string, which is what we're going to do here, to pull back the number of processors. Either way will work nicely. So on this particular machine, we have 16 processors. Just in case you're having to run applications on machines which are still 32-bit, it's very useful to find out whether a machine is 32-bit or 64-bit. 32-bit machines and operating systems can only access a maximum of 4 gigabytes of memory. So even if you do have more than 4 gigs installed, you may not be able to use it all. While there are fewer and fewer machines left now with 32-bit operating systems, it's useful to find out what you have on the system. So we'll create another function to work out if it's 32 or 64-bit. Now this one unfortunately is a little bit more verbose, and we have to delve into the Windows API again. So we're using the native system info user-defined type to pull back information from the Windows operating system. Now to save a little time, I'll just paste this entire section of code in and I'll explain what it's actually doing. So the get native system info pointer we're setting up here is used to get the process address of this particular routine within the kernel DLL, the core of Windows itself. And if this pulls back a true, then we're actually calling it. I'll fold this around so you can see it. And we're using the system info as a repository of the information. Now what we're pulling back here is the architecture, and we're also pulling back the number of processors. Now we already have that information, but all we're doing here is working out what the architecture actually is based on these constants. So it's either going to be an AMD 64-bit, or it's going to be either an Intel or an AMD 64-bit, and if it's neither of those, it's a 32-bit system. And we'll set this up at the top. This is our repository for the information coming back. So we save this and we run this again. We will find it is indeed a 64-bit system, as you would expect. So we've now determined quite a bit of information about what the computer is that we're actually running this on. The thing we haven't looked at is the disk drives. Now, the computer itself may have a single disk drive or it may have multiple disk drives. And there's two bits of information we're interested in. One is the size of each hard disk, and the other is how much free space is on each hard disk. So what we can do first of all is we can have a look at the C drive. Now, it's usual but not always essential that Windows is installed on the C drive. It may be on a different one, but more often than not it's on the C drive. So one thing we can actually do is we can print out using the disk size command in PowerBasic to pull back the information for the C drive. And we can do this quite easily. I fold this around so you can see it. So what we're doing here is we're using the disk size option, telling it it's the C drive we're interested in, and it's going to return the size again in bytes. And we're dividing that by 3 sets of 1024 to turn the bytes into kilobytes, then to megabytes, and then to gigabytes. And what this will tell us is what the physical size, the maximum size of the C drive actually is. If we try running that now, we'll see that the C drive in this particular machine is 118 gigabytes. Now that's useful, but we don't know what other drives this particular machine actually has. But what we'll do first is we'll work out how much free space is actually on that C drive. Now, there is a disk free command that comes with PowerBasic that does that job very nicely. And if we do the same as we did before, just so you can read, using the disk free on the C drive, dividing it to make sure it's in gigabytes, and then if we run that now, we'll see that the C drive has indeed got 50 gigabytes free. Now that's fine, but how do we tell what other drives? Is there a D drive? Is there an E drive? Well, we could quite happily put this in and change the C to a D and see what the system returns. And we do indeed have a D drive, which is quite a bit bigger. But there's a nice easy way of finding out all the drives we have. So what we're after is something that will pull back all the drives we have and what sizes they are. So we'll create a new function that performs this little function. Of course, ideally you could actually just step through the letters of the alphabet until you get nothing back. For example, if you look at the disk size command in the help, if we try to run it on one that doesn't exist, let's see what we get. Let's try running this on a Z drive, because I know in this system there is no Z drive. And we'll comment this line of code out for the moment. So if we run that, we see that in this case, the Z drive has 0 gigabytes on it. So that would be an easy way. You could cycle through every single letter to find out what they are. However, you wouldn't know what kind of drive this was. Was it a fixed disk? Was it a DVD? Was it a removable drive? Was it even a RAM disk? So that's what our new function is going to do. It's going to pull back all the drives using the Windows API. Now I'm going to create a new library for this one because it's all about drives. So let's create a brand new library and we'll call this one drive info. And we will save this one into our libraries. Yeah, this is something you can actually build on. Now we're going to create another user-defined type on this one, into which we can actually populate our information, and we're going to use another Windows API call, so we'll just declare that one in here, again coming from the kernel, and the routine we're actually doing is get drive size. So let's have a look at get drive size, and to save some time I'm just going to paste the whole of this in and then go through it. So we're calling get drive size, and we're going to be passing it back as a string. Now what we've done in here, we've created some temporary variables, which I will fold around so we can see what we're doing. Now I'm working on an assumption there won't be any more than 100 volumes on the machine, which is reasonable, but you can always up that number if you think the machine has a great number of disk drives. And we're actually going to cycle around with the result of what comes back from here. So this is pulling back the logical drive strings. It will give us back a list of all the drive letters for all the drives attached to this particular computer. And then we're just cycling down from there to the count of it based on the null delimiter. Now what we were interested in was picking back the drive type. What kind of drive was this? And this allows us to actually identify which drives are fixed, which are effectively mapped drives onto some network drive, because you don't want to count them, which ones are effectively CD-ROMs or DVD drives, which ones are RAM drives, and which ones are removable disks. And everything else would basically be unknown. So what we're doing there is we're getting the volume information on each of the drives, and we're specifically interested in fixed drives and removable disks. And for this we're pulling back again using the disk size. Since we know the drive letter name, we can use the disk size command to pull back the details of how big the physical disk is. We can do exactly the same thing for the free disk space. So since we've got a new library, we'll have to add this library to the top. And let's do a quick compile on that, which is successful. So if we try running that now, we'll see in this case that not only have we a C and D drive, which we knew about, we've also got an E, a G and an H drive. I happen to know on this machine that the G and the H drives are removable USB drives. Now if we needed, we could actually pull back that information based on the type. So you could break up this function to return more than just the size of the drives. So this has pulled back some basic information about the computer our application is actually running on. This has just touched the surface of computer forensics on a machine. But that's it for today. Thank you for watching.